Next, coming to the tab 3. So tab 3 problems are bars with varying steps. As you can see, the diameters are different, areas are different in the figure. So, and it's being pulled by a force having different lengths. All three sections have different lengths. So we'll call each one as section 1, section 2, section 3. So section 1 is area 1 and length L1. Section 2 is area 2 and length L2. Section 3 is area 3 or length A3. Or similarly, diameters D1, D2, D3 for sections 1, 2, 3. But the force is common here. We have only one force here, which is pulling. So simple, just you have to separately calculate stress and strain elongation for each sections, and finally we have to add the elongation to get the total elongation. So very simple. So first, considering section 1, as you can see, section 1 bigger one. So for section 1 separately you have to calculate the stress sigma 1. So sigma 1 is F is common, F upon area 1 A1. So sigma 1 is F upon area A1 for section 1. I'm talking about section 1. So we get the answer Newton per mm square. So calculate this separately. Then again, next for section 1 again, calculate the strain epsilon 1. So epsilon 1 we can also find by the formula sigma 1 upon E. Sigma 1 upon E, if E is given, we can find the strain also using this equation. Third, now elongation of section 1 only. So delta L1 will be F is common into L1 E1 E if E is also is common. So elongation of section 1 only is delta L1 F into L1 all upon area E1 into E Young's modulus. Similarly, the same thing we have to carry out for section 2. Section 2 again, find sigma 2 is F upon A2, that is area 2, area of cross section area 2. Strain epsilon 2 is we can use the formula sigma 2 upon E if E is given, and third is elongation delta L2 is F into L2 upon A2 into E. F is common, L2 is length of second section, E2 is area of cross section of second section, E is common. Similarly, for section 3 again, same you have to calculate for the same formula, sigma 3 equals to F upon A3, that is third area. Second is strain epsilon 3 is sigma 3 upon E. Third elongation delta L3 is F into L3 upon A3E. F is a force, common force. L3 is third length of section 3. A3 is of area 3, section 3. Easy. So these are the elongation of all separate sections. Therefore, the total elongation of the bar delta L will be sum of the three lengths. So delta L1 plus delta L2 plus delta L3 will give you total elongation delta L. Or we can write it in a simpler form, FL1A 1E plus FL2 A 2E FL3 A 3E. So if F and E are common, we can take it out common into L1 by A1 plus L2 by A2 plus L3 by A3. We can use this formula also to find the change in length, total elongation of the bar in simple way. Suppose the bar is made up of different materials and different, then E will change. So E value will have, Young's modulus capital E will have different value. So at that time, change in length will be F into F is common, F into L1 A1 E1, plus F into L2 A2 E2 plus F to L3, E3, E3, where F only one is common, rest all things are different. So F into bracket L1 plus upon A1 E1 plus L2 upon A2 E2 plus L3 upon A3 E3. So we'll take a simple example here. So a composite bar made up as shown in the figure is subject to tensile load of 30 kN. The extension observed is 0.74 mm. Find the Young's modulus of the brass if the Young's modulus of steel is 2 × 10⁵ and stress in the materials. So as the details are given, so bigger is 30 mm diameter, smaller is 20 mm diameter. Bigger is steel, smaller is brass, 800 mm length, 600 length is brass, 30 kN force. So composite bar as shown in figure. So P is 30 kN or 30,000 Newton. Delta L is 7.74. Steel is given 2 × 10⁵ MPa. LS EIS refers for steel. Length of steel is 800. DS diameter of steel, that is 30. LB length of brass 600. DB diameter of brass is 20 mm. So the total elongation of the bar delta L will be delta L1 or delta LS plus delta LB. Yeah. So total elongation is something but 0.74, and delta L is another P into LS AS ES plus P into LB AB EB. Only P is common, so P taking P as common. So P is common, so 0.74 equals to P, which is common, into bracket LS AS ES plus LB AB EB. So load, taking the load to the other side, so dividing by 0.74 divided by 30,000 equals to 800 pi by 4 30 square into 2 × 10⁵ plus 600 pi by 420 square into EB as it is, which is unknown. So simplifying all these things by our calculator, so we can easily get the Young's modulus of brass, that is 1.005 × 5 Newton per mm square. Now also to find stress, so stress in steel is sigma s upon P upon AS. So 30,000 into pi by 430 square equals 42.44 MPa. Stress in brass sigma B equals to P upon AB. So 30,000 into pi by 420 square, 95.95 Newton per mm square. So we'll take one more example with the 3 sections. An axial load of 140 kN is being pulled down 3 sections. Young's modulus for all the 3 sections is common, that is 2.1 × 10⁵. Determine stress in each section, total elongation and maximum stress in the material. So we'll take each section one. So we'll take stress. First we'll find stress in each section. So stress in section AB, smaller section AB, is load upon area of cross section. So load is 140 × 10⁵, and area is pi by 4 into 40 square. So we get 111.4085 Newton per mm square. Stress in section, the middle section, that is BC, sigma BC equals to P upon area of BC. So load is 140 × 10⁵ pi by 4 60 square. We have 49.515 Newton per mm square. Similarly, section in the last section, that is the bigger section CD. So P sigma CD is P upon area of CD, that is 140 × 3 upon pi by 4 100 square. We have 17.825 Newton per mm square. Now to find the total extension bar, sigma delta L equals to delta L of AB, delta L of BC, delta L of CD. So delta L of AB So here we can rewrite the equation as P by A. AB is sigma AB into LB upon E plus P upon ABC is sigma BC LBC E, P upon ACD, that is sigma sigma CD LCD upon E. So taking the E as common, 1 by E as common, and multiplying other two things. So we have 1 upon E, that is 1.2.1 × 10⁵. So we have the extension bar that is 0.1837 mm. So looking at the three stresses which we found in earlier, so maximum stress occurs at the smaller section, that is section AB, and that is 111.48. So maximum stress occurs at section AB. So we'll take one more example. A bar is shown in a figure that is with a tensile load of 150 kN. If the stress in the middle portion is 160 Newton per mm square, determine the diameter of the middle and find the length of the middle portion. If the total elongation of the bar is similar to 0.25 mm, Young's modulus is equals to 2 × 10⁵ Newton per mm square. So first to find the diameter of the middle portion. So stress is given in the middle portion, that is 160. So stress at the middle portion is sigma, we'll call it as section 2, and this was section 1. So stress at the middle portion, that is section 2, is sigma 2 is P upon A2, that is 160 into 150 × 3 upon 5/4 d2 square. d2 is 34.55, and length of let the length of the middle portion be 450 minus L2. So we'll call this middle portion as L2. So 450 minus L2 will be length of the middle section. So extension of the bar delta L is P into 450 minus L2 upon A1 plus P into L2 E2. So 0.25, 150 times to 3, 450 minus L2 pi over 4 100 square into 2 10 to 5 plus 150 times to 3 into L2 pi over 4 34.55 10 to 5. So we get substituting taking common, we can get L2 as 293.862 mm.